talking about sequences today, and next week we'll kind of extend into that. But you guys have been working pretty hard here, and it's kind of nice. You're kind of starting on to chapter 8. We're not going to fully go into everything in chapter 8. We're just going to talk about some of the basics there. Sequences, we've already kind of talked about those earlier in the year. You guys have been working with those for a while. We're just going to, re-go over some of that. Some of this will likely be a review. If you remember some of that stuff when we were talking about integrals and where we needed to add up a bunch of stuff. But it's always good to review things as well. So just a little bit of review. A set, if we talk about a set of numbers, is just a list of numbers. It doesn't have to be in any particular order. And you just kind of set those numbers down, right? You just write them down. There doesn't need to be any repetition in a set. That's perfectly fine, but that's all a set is. It's just a list of numbers. There's no necessarily rule or anything to it. More specifically, a sequence is a list of numbers, again, but in a particular order. And sometimes repetition is important in a sequence if something is maybe alternating or something else, but you can get repetition in a sequence and the order is important. They're in a particular order. So notice these two have the same numbers, but this one is a sequence. I guess this could be a sequence as well, right? I mean, we're just adding one every single time. But here it's in a particular order. So they are not the same list. They are not the same sequence, though these two would be the same set, right? So that's a little difference between sequence and set. And then series we'll talk about some more next week. That is when we add up an entire sequence, when we kind of sum everything up, which in this case, if we summed everything up, we'd always get 0. But to look at, kind of how those things work. We've talked about some of this before, but there is two different forms. There's recursive form, which isn't as useful for calculus because that gets a little harder to do. Because recursive form, you need the previous answer in order to get the next answer, right? We need to do that. So in here, you need to always say what's the first thing going to be in recursive form. So we wouldn't really have to apply that. This is saying the 0th term is 0, right? So we set that. And then we just kind of work through here. If we make, and then if I want to move up to the next term, well, this says I need an 1. Oops, I forgot my little -1 up here. Oh, see if we can put that in there. Oh yeah, it's going to do that. But so we need that. So here we go, -1 to the n-1. So that means -1 to the 0 power, because we would subtract 1, which is just 1. And this says we take our number times that value. So 1 times this is 1, and then we add it to the previous term. So we multiply these two, add it to 0. Well, that's 1, right? And then we move up to the next one. Well, now we take -1 to the -1 to the first power is -1. We'll multiply these two. That's n times this stuff. Multiply these, we get -2, and we add it to this one. Oh, that's -1. And then we move up to the next one. And what's going to happen usually when you see this -1 to a power, it's just going to alternate. This will be -1 squared, -1 cubed, -1 to the 4th, -1 to the 5th, and so on, right? That's just going to alternate. And then what we do is multiply these two, add it to this one. So 3 plus -1 is 2. -4 plus 2 is -2, and so on, right? And what you see is this is the formula that I used to generate the sequence back here from the example, right? This was the formula that I used to generate that sequence, right? It's kind of keep alternating there. So it is important there was a pattern there, although I was using a recursive formula to get that. All right, so recursive formulas are fine, but they're not as useful in calculus. What we usually want is what's called an explicit formula, or something in explicit form. Okay, so in here, I gotta find where I put my calculator. Well, I'll just use Google or something. But so on here, when we work through this one, all right, we'd start, maybe we try to plug in 0. Oh, but we'd have to do 1 divided by 0. Actually, we can't do that. And then we just kind of work through. If we plug in 1, 1 plus 1 to the first power, that's 2. Here we'd get 1 plus a half squared, right? So maybe I'd go over here and say, well, I wonder what 1.5 squared is, and that's 2.25. Okay. So now I go back in here and say, all right, that's 2.25, and so on, right? You guys can go ahead and do that. This would be 1.33 cubed, 1.25 to the fourth, and so on. We'd keep going. Now, what we'd want to see is, does this sequence converge? That's kind of a leading question. Does it eventually get somewhere, right? Does it converge? Meaning, does it get to a particular number? Is the limit discrete, right? It's called a discrete if it becomes a particular number. It's called infinite if it does not, right? If it goes to infinity or something like that. And that's called divergence. Same thing with the improper integrals, very connected to that, so that we use the same language. Converge if we get a number, diverge if it becomes infinite and does not. So there are three kind of particular ways we can check for convergence. We can just go ahead and straight up do the limit, right? If it's in explicit form, we just take the limit of it, see what it becomes, and if it's a number, well, then that's what it converges to. You can also use a version of the squeeze theorem, which we haven't gone over in a while. We went over that back in first semester, but I'll show you an example of that again. Or we can talk about these bounded monotonic sequences. Sounds pretty complicated, kind of a mouthful, but they're actually not too bad. Sometimes it's a little tough to check if they're monotonic, but it's not too bad. We'll talk about that in a sec. So for the first one here, checking the limit of a function. So we'll go back to that example here, this a to this stuff. Well, what we would do is just basically think about that as a function, right? So there is a difference between this and the function. They are not the same thing, but if the function goes to a particular thing, then the sequence is also going to go to a particular thing. And I'll show you what I mean by that difference here in just a second. But here what we would do is, we'd take the limit of this. Actually, let's just grab this thing so I don't have to retype it all. This part here, you guys have done this limit. We've done that before. Back when we were doing L-Hop's rule, you take the natural log of both sides, knock the x down, and then use it L-Hop to get all the way through that. Eventually, this becomes E. It's actually one of the definitions of E in that case. So what this then implies is if this thing particularly goes to E, then that means that A sub n also goes to E, right? We could actually make this a little bit better. Let's say as as n goes to infinity, then a to the n goes to E, right? We'll make that a little more defined, right? So that we have that in our notes there as well. Okay, so that's the basics of it, right? If you have a function, do the limit. Sometimes you have to use L-Hop's rule in order to get that limit, or just evaluate it like we normally would. Okay, so that's the whole thing there. The second way is what's called the squeeze theorem, right? And we haven't talked about that for a little while, but what the squeeze theorem says is that if you can find, if we can find some function that is always below our particular sequence, and you can also find a second function that is above that particular sequence, and these two bounds, these two outside things, the one that's below and the one that's above, also both converge to a particular thing, then the stuff in the middle has to go to that particular spot as well. They have to kind of converge together. So in here, we'll look at an example of that, right? So I'm going to look at this sequence. A sub n equals 1 to the, or negative 1 to the n over 1 over n factorial. Excuse me, lost track of what I was even saying there. It gets a little confusing talking to yourself over and over. So what I'm going to do is just grab this so we can at least kind of take a look at what are the first few things going to be. We could do 0 because, again, 0 factorial is defined as 1. So we can, in fact, do that, right? This would be 1 times 1. And then we just kind of go along here. This one here, in this case, would be 1 factorial, sure. But it'll be negative 1 in that case, okay? And here if we do, 2 factorial is 2, because that's 2 times 1, and then we will go back to being positive. It's just going to alternate positive, negative, positive, negative. This will be 3 factorial, so it will be, oh, actually not 2, 1/2, excuse me, 1/2 there. 3 factorials, 3 times 2, which is 6, and that will be negative, so negative 1/6. Now we'd have 4 times 3 times 2, so that'll be positive 1/24. And it kind of seems like this thing is going to eventually become 0, but we can't say that for sure, right? We have to prove that, so either we have to do the limit, which in this case, it is rather difficult to do limits when you have this type of alternating thing. That can often, that's what makes things difficult. If we didn't have this here, then certainly it would go to 0. That's one thing that we would have pretty much there. So we can do this in different ways, but what we need to have happen is we need to bound this a to the n. So what I'm going to do here is, let's just make a new sheet, and we're going to say, well, we need something that is always bigger than a to the n and something that's always smaller than that. So something that in particular is going to always be larger than that is, as I kind of mentioned, you know, we can kind of do a little bit of a cheat method here and just say, well, something that's always going to be larger is the positive version of that stuff. Like this is always going to be bigger because it will always be positive and it will match up all of the time. So we have that. And then kind of the cheat method here, the one that's always going to be smaller is going to be the negative version of that, right? So we don't have to worry about the oscillation, right? We're sort of getting rid of that oscillation. And what we can find here is that this thing is going to approach 0, and so is this part. And since both of these approach 0, right, so we can kind of type that in here. Since both, what do we have? B, oops, and, oh, well, it doesn't like that. Let's just do this. And so since both of those go to 0, then AN has to go to 0, right? That's kind of the basic idea there. And we can see that these two things go to 0 in this case because this denominator is going to keep getting larger and larger and larger. Therefore, it has to go to 0, right? That's something that we've talked about before. And it's going to happen here as well. This is going to keep going to 0. And so it's bounded, right? This one's always below. This one's always above. This stuff's going to 0. This stuff's going to 0. So even though this thing is bouncing up and down, it's bouncing up and down slower and slower and slower as we get there. So that's a little bit with the squeeze theorem on there. The last one that we're going to talk about, last type here, is what's called something that's monotonic. Okay, something that's monotonic, and I believe we kind of talked about that as far as functions go. Same thing with sequences. Something that is monotonic means that it's always increasing, or perhaps it's always decreasing, right? It never does any sort of bouncing. It just always goes either down or up, right? Never changes in that case. So here's a few examples just to look at, you know, whether they're monotonic or not. So if we looked at the first one here, 3 plus -1 to the n, again, here's a clue. This is likely not going to be monotonic because this -1 to the n, that's going to be, you know, +1, -1, +1, -1. And in fact, here, that's exactly what happens. When we make this thing 0, it will be 3 plus 1, which is 4. And then the next one will be 3 plus -1, which is 2. And then it will just alternate back, because now this is going to be -1 squared. So it'll be 3 plus 1, 3 minus 1, 3 plus 1, 3 minus 1. And this is just going to keep bouncing back and forth. 2, 4, 2, 4, 2, 4, 2, 4. This one actually has no bound, like no limit. All right, it's not going to like tend to anything. It's just going to infinitely repeat between 2 and 4. So this one is not monotonic, right? It is not monotonic. Maybe I should put that in there for emphasis. Not monotonic. All right, we want to make sure we have that in there too, right? So there we see that that is not monotonic. If we check the next one here, right, we could start plugging in stuff. If we plug in 0, we actually get 0. 0 divided by 1. Plug in 1, we get 2 over 2. Okay. Plug in 2, we get 4 over 3, which is a little bit bigger, right? Plug in 3, we get 6 over, lost track of it. Okay, 6 over 4, which is 3 halves, which is a little bit, bigger, 1.33, 1.5. Plug in 4, we get 8 over 5, right, which is a little bit larger still. And so the thought is, well, this seems to be monotonic. It seems to be increasing, at least for the first few terms. But if you want to claim that something is monotonic, what I would like you to do is to prove that it is monotonic. And so I'm going to show you how do we prove that this is, in fact, monotonic. And how we do that is we just take this function and we say, okay, I have my evidence. I'm pretty sure it's increasing. Let me stop that. Pretty sure it's increasing, right? We did a little bit of stuff, we checked. So I'm pretty sure that the next number will be greater than this one. And here's how we put that. I'll put 2 to the n plus 1, all divided by 1 plus n plus 1, because this would be the next term, right? We're just going to put it sort of in equation form. And the thing is, we're not actually sure if this is here, so I should put like some question marks next to that. Like, I'm not 100% sure, but I'm pretty sure it is for the first few, so I can at least put that in there. And then here we just work this through and see if we can get to a point where we can say, yep, for sure, this will always hold. And so that's kind of like manipulating stuff around here. So for example, this would be n plus 2, n plus 2 in there. And so we could sort of multiply stuff across. We could cross multiply. And the reason we can cross multiply here is this is always going to be a positive number because n has to be bigger than 0, right? So this will be positive, so will this. So when we multiply those things across, we're not going to change the direction of that symbol, right? We're not going to do that. So then here I can multiply, there we go, multiply this n plus 2 over here and multiply this 1 plus, or n plus 1 again, over here, right? So I'm going to space this out a little bit so that we can actually see those things. And then the next part would be to distribute everything, right? This side here would be 2n squared plus 4n. So we'd have 2n squared plus 4n. And then over here, well, first we distribute this part. That would be n squared plus 2n plus 1. Now we're going to double everything in there. So let's actually, so we're going to double all that stuff. So we have 2n squared, 4n plus 2. Now we can see, oh, actually, hang on, yeah. Once we've distributed all of that stuff out, we can see, oh, for sure, this stuff over here is always bigger than the stuff over here because it's being, has 2 added to that. So just to emphasize this, right, this one here, let's take this guy, and we can compare these two things, right? It has the same stuff in it on both sides. Maybe we'll make that in like a nice gold or something a little thicker. So this means it must be true. The next number, this side, will always be larger than this one. So this first part has to then hold. If you can't get to something where you can see, oh yeah, for sure, this is always bigger. I mean, when I look at this first part, I don't know for sure if this is bigger or not. Not until I've distributed and can see, oh yeah. Or you could think about like we cancel these out and say 0 is always smaller than 2, right? That will always be true. So in fact here, yes, this is a monotonic sequence because we always get something that's larger over here. And so I do want you to prove that something is monotonic. If you have evidence for it, you do have to prove that. And then the last one, that last example, we take a look at this, and what we do is just plug this stuff in, right? If we tried to plug in 0 here, in fact, we couldn't, because that would be 2 to the 0, which is 1 minus 1. We'd be dividing by 0, which is actually not okay on that one. Now, some of you guys might look at that and say, oh, hey, wait a second, we get 0 over 0. Can't we do LHOP on that? And you can do LHOP if it's a limit approaching 0, right? If it's limiting, if it's getting close to 0. But in this case, we can't do LHOP because we're just strictly plugging that in. We're finding a singular value. As we talked about before, 0 over 0 as a value is just simply undefined. So in this case here, you can't plug in 0, and so we'd actually start at 1. And we'd say, well, this is actually 1/2 because that's 1 squared over 1. And then we just kind of keep going. The next one would be 2 squared is 4 over, in this case, 4 minus 1, 3. So it got a little bit larger, right? It actually increased here. And then in this one, when we plug in 3, we get 9 over 8 minus 1 is 7. So 9/7, right? That's what we'd have there. Then we could keep going, but actually we'll look at these two, 4/3 and 9/7. So I'm going to go actually back here and say, well, let's see. If we do 4/3 minus 9/7, right, it gets 4/3 is actually a little bit bigger than 9/7 by just a bit, not much, but it is a bit bigger, right? Because when we subtract those. So it got larger this way and then smaller here. So it's not monotonic. We can see that happening right here, that it's not monotonic. So let's maybe emphasize that here. We'll say, you know, it got larger this way. Now we'll make that red. It got larger, but then over here, it actually decreased and got smaller on this one. So we can see it is not monotonic in that case, right? Actually, I'm going to grab this one as well, right? Same thing as A. This is not monotonic because we saw, actually it turns out in this one here, if you omit this first term, it does end up being monotonic and decreasing there, but not a big deal. But that's how we check for monotonism. I think that's maybe a word. We'll try it. Last little bit here is if a monotonic sequence could be bounded, right? It might not be always bounded, but we want to check if it is. Very basic language. Bounded above means there is some number that this sequence will never get larger than. Now we bounded above. Bounded below, there's a number that the sequence will never get lower than. So there's that. And then if we say the word bounded without saying above or below, that is implied then that it has a bound on top and bottom. Yeah, that's what we mean by the word bounded. And the key piece is that bounded monotonic sequences will always converge. It kind of makes sense. It's basically the squeeze theorem, right? If you have a top and a bottom thing and it's always, you know, going towards that bound, it has to eventually become whatever that boundary is, right? Or at least get close to that boundary. It doesn't necessarily always have to be that boundary in particular, but it's got to go to something, right? It's always leading to something. So here's an example here. This one is monotonic. It is always decreasing, right? 1 over 1 is 1, then we get 1/2, and then a third, and then a fourth, and a fifth, and so on, right? In that case there, it is monotonic. We can see, we just kind of talked about that. I mean, we could prove it too, but we pretty much have evidence there. And it's also bounded, right? It's bounded above by 1, right? It can't ever get larger than 1. And it's also bounded below by 0. So it is bounded and monotonic, therefore it has to converge. And in fact, this one, you guys know, converges to 0. Here's an example of one that is monotonic. However, it is not bounded, right? This one will always keep growing larger and larger and larger. It is bounded below, right? It is bounded below by 0, in fact, right? This thing can never get smaller than 0, but it has no upper bound, right? It will just keep growing and growing and growing. So this is monotonic, not bounded, and you could do LHOPs to find, oh yeah, this is actually diverges. You can't get that thing there. And then a very simple example, this one's bounded, right? It's bounded above by +1 and bounded below by -1, and it just bounces between the two. It's not monotonic, and we saw one very similar to that, the one that bounced between 2 and 4, right? 2, 4, 2, 4, 2, 4. I mean, that one is also bounded by 2 and 4, but it's not monotonic, so therefore it doesn't necessarily. So you need to be both monotonic and bounded if you're going to use that claim to say that something converges, right? So again, more so on this one, just a lot of terminology. The math behind it is not too bad, right? Most of the time it's just doing limits. Eventually next week we'll get into, you know, how do we use integrals to check I want to get the words right, to get a series, right? Because we're adding up lots of stuff. Well, that's kind of like an integral. So we can use integrals and series kind of go together, and that we'll get to next week in there. And then tomorrow what we'll post is a little bit of an activity that will lead into next week. So you guys, the activity is not going to be graded, but you can give it a try, something to try out over the weekend, see if you can solve a couple of them. But otherwise, let me know if you got some questions, and I'll see you next week.